Okay, take a minute to look at this function f of x equals x squared. So this is the function that takes whatever number you give it and gives you back that number squared, that number times itself. So f of 3 would be 9. And f of negative 3 would also be 9, because negative 3 times itself is 9. A negative times a negative is positive. F of 10 is 100, and f of negative 10 is also 100. F of 17 is 289, and f of negative 17 is 289. So this always happens, where if we plug in a positive number, we get something. If we plug in the negative of that number, we get the same thing. So for any x, f of negative x is equal to f of positive x. And when that happens, we call a function like that an even function. And the reason for that name, it's inspired by the fact that when you have x to the 2 power, or x to the 4 power, or x to the 6 power, or x to any even power, it works like that. Take x to any even power, it kills off the negative and gives you the same thing when you plug in a negative as when you plug in a positive. There are other even functions besides just x to an even power, but that's one example of a function that works that way. So a function that's true of is called an even function. Now look at the function that gives you whatever number you put in to the 3rd power, the cubing function. F of x equals x cubed. So f of 3 would be 3 times 3 times 3, 27. And f of negative 3 would be negative 3 times negative 3 times negative 3, which is negative 27. Remember, a negative times a negative is positive, times a 3rd negative is negative. F of 10 would be 1,000, and f of negative 10 would be negative 1,000. F of 17, 17 cubed, would be 4,913. And f of negative 17 cubed, would be negative 4,913. So notice what's happening here. When you plug in a negative number for x, you get not the exact same thing that you get when you plug in a positive number, you just get the opposite of that thing. F of negative x equals negative f of x. Like f of negative 17 equals the negative of f of 17. And a function that works this way is called an odd function. So examples of functions that do work this way would be if you have x to some odd number power, like x to the 3 power, or x to the 5 power. Now, how does that relate to the graph? Well, an even function is always going to have a graph that is symmetric about the y-axis. That's because when x is a positive number, you get a certain y-coordinate to go with that. When x is a negative number, you get the exact same y-coordinate to go with that. And an odd function is going to have a graph that is symmetric with respect to the origin. So every point on the graph, you've got your x-coordinate, and then the y that goes with it is f of that x. If you have another x-coordinate that is the opposite, negative x, the y that goes with that is f of that negative x, which is the opposite of f of x. So let's look at some examples. Is this that we were looking at earlier, f of x equals the square root of 16 minus 4x squared, is this an even function, an odd function, or neither one of those? Well, it is symmetric with respect to the y-axis, so it must be an even function. Now we could also figure that out from the equation. Notice the only x in the equation is being squared, and that's going to kill off the negativeness. If we plug in a negative for x, if we replace x with negative x, f of negative x would be the square root of 16 minus 4 times negative x squared. But negative x squared, negative x times negative x, is the same as just x squared. So f of negative x is really just the same as f of x. What about this one that we were looking at earlier? F of x equals 3 minus the square root of x squared minus 9, whose graph looks like this. This graph is symmetric with respect to the y-axis, so that means this would be an even function. Again, notice that the only x in the formula is being squared. What about this function? Yep, it's another even function. We can see that on the graph because of the y-axis symmetry, and we can also see it in the formula because x is being squared. What about this one? We haven't seen this before, but here's what the graph looks like. Is this an even function, an odd function, or neither one of these? Well, this graph is actually symmetric with respect to the origin. That means we could rotate the whole thing through 180 degrees, and it would match up with what we started with. So every point up here in quadrant 1 with a positive x and a positive y is going to have a matching point down here with a negative x and a negative y. So we've got a point, like if we've got a point 3, 6, we also have the point negative 3, negative 6. And if you wanted to check that from the function itself, the equation that defines it, you would do that by calculating f of negative x. That is, you replace every x in the formula with negative x and work out what that gives you. When you take a negative x to an odd power, it comes out negative. So this would be negative x to the fifth. So I pulled the negative out in front. Here we got negative x to the third, and you pull the negative out in front, but then it would be minus a negative, which is the same as plus a positive. Pull the negative out in front here. Then from all three of these terms, if I factor out a factor of -1, or just a minus sign, it's minus the quantity 0.004x to the fifth, minus 0.224x to the third, plus 3.69x. And that, inside the parentheses, without the minus, is what f of x originally was. So that shows that f of negative x is equal to the negative of f of x, which means, by definition, it's an odd function. What about this one? F of x equals 6 over x minus x over 5. It's not symmetric with respect to the y-axis, but is it symmetric with respect to the origin? Well, yes it is. It's got that origin kind of symmetry, so this is an odd function. And again, we could look at f of negative x, where we replace each x with minus x. We could factor out a minus sign, and it would be minus f of x. What about this one? Is this an even function, an odd function, or neither? Well, it's not symmetric with respect to the y-axis, and it's not symmetric with respect to the origin, so it's neither one of those. Notice, by the way, that one of the points on the graph is 2, 7. So f of 2 is 7. You can also test that in the formula. And f of -2 is 11. Now, if this were an even function, you'd expect f of -2 to be the exact same thing as f of +2, like 7. And if this were an odd function, you'd expect f of -2 to be the opposite of f of +2, so -7. But it's neither one of those. So lots of functions are neither odd nor even. Now we're going to talk about increasing and decreasing functions. What does that mean? Well, for a function to be increasing means that the bigger a number you plug in, the bigger a number you get out. Or to put that a little bit more technically, if you plug any two x's into the function, where x1 is smaller than x2, so x2 is the bigger one of those two numbers that you're putting in, f of x2 is going to be the bigger number that comes out. So when you plug two numbers into the function, you get two numbers out that have the same relationship. Smaller number going in gives you the smaller value coming out. The bigger number coming in gives you the bigger number coming out. For a decreasing function, it's the other way around. The bigger a number you plug in, the smaller a value you get out. And the only other thing that could happen is where no matter what you plug in, you always get the same thing out. And that would mean that a function is constant. Now, how that relates to the graph is if a function is increasing, that means that the bigger x is, the bigger y is. So as you go along from left to right, you're also heading upward. If a function is decreasing, that means that the bigger x gets, the smaller f of x, which is the y-coordinate, gets. So as you go along from left to right and your x's are getting bigger, you're headed down because your y's are getting smaller. And then if you were just going right straight across, then the function would be constant on that interval. So here are some simple examples. The function 3x takes whatever number you give it and gives you 3 times that number. The bigger x is, the bigger 3 times x is. So if x goes from 1 to 2 to 3 to 4, 3x is going to go from 3 to 6 to 9 to 12. And x minus 10 is an increasing function. The bigger x gets, the bigger x minus 10 is going to be. If x goes from 1 to 2 to 3, x minus 10 is going to go from negative 9 up to negative 8 up to negative 7. And the square root function. The bigger x is, the bigger the square root of x is. In each case, the graph is headed upward as you go along from left to right. Here are a couple simple examples of decreasing functions. Negative 3x, the bigger x is, the smaller negative 3 times x is going to be. So if x goes from 1 to 2 to 3 to 4, negative 3x is going to be going from negative 3 down to negative 6, down to negative 9, down to negative 12, and so on. So that's a decreasing function. And 10 minus x, the bigger x gets, the smaller 10 minus x is going to get. If x goes from 1 to 2 to 3 to 4, 10 minus x is going to go from 9 down to 8 to 7 to 6. So these are decreasing functions. And then you can have a function that's increasing part of the time and decreasing part of the time. For example, the squaring function. If the number you plug in for x is a positive number, if you're plugging in positive x's, the bigger x gets, the bigger x squared is going to be. As x goes from 1 to 2 to 3, x squared is going from 1 to 4 to 9. But if the numbers you're plugging in for x are negative numbers, then the bigger x is, the smaller x squared is going to be. So as x goes from negative 3 to negative 2 to negative 1, always negative but getting bigger, x squared is going from 9 down to 4, down to 1, getting smaller. So we would say that this function is decreasing on the part of its domain where x is less than 0. That is the interval from negative infinity to 0. And it's increasing on the part of the domain where x is greater than 0, on the interval from 0 to infinity. Now careful, we always talk about increasing or decreasing on some particular interval. And an interval refers to a section of the function's domain, like a section of the x-axis, an interval of x's. So you have your starting x and your ending x. So I'm going to end this video here. We're going to come back and look at some more examples. We'll see if we can tell from a graph where a function is increasing and where it's decreasing.